Welcome back. So in this third lecture, I'll be talking about certain properties of networks which we haven't dealt with so far, which I would call meso-level property. Have people ever heard the word meso before as opposed to macro and micro? Yeah, so meso means middle. So macro is large, micro is small, and meso means intermediate, right? And so I'll be talking about certain meso-level properties, and what I hope to make it clear is that why these meso-level properties are so ultra important in understanding how certain networks behave the way they do. So the question is, as always, how do you characterize the important properties of a network? So we have already in the previous lectures dealt with the macro properties, right? So these are global properties in the sense that you're asking questions about the entire network. Questions like, how can I go from one point of the network to another point of the network? Okay, what's the shortest path length? Or it could be about, how tightly coupled the entire network is. So any question you're asking about the entire network would be a macro or a global level property. By contrast, in micro level properties, you're asking questions about your neighborhood, your immediate neighborhood of a node. So for example, how clustered is your particular neighborhood? How many of your neighbors are also mutual neighbors? So that's a very, very local micro question. Or you could ask, are there motifs? So motifs are, very frequently occurring patterns of connections between, let's say, a set of 3 or 4 nodes. So if you find that, very often you find links between 3 or 4 nodes which look like this, then it could indicate that there is something about this pattern of connections between 3, 4 nodes which is functionally important, which does something to their function. And in this lecture, what we'll be dealing with are intermediate scale properties, or what I call meso properties, which is neither looking at local neighborhoods of individual nodes, nor are they looking at the entire network. Rather, it's looking at groups of nodes and how they relate to other groups of nodes. Okay, so that's the sense in which I mean meso or intermediate. So it's not at the level of the entire network, it's not the level of a single node at its neighborhood, but rather one set of nodes, how do they talk to another set of nodes, and how do they communicate with each other, and so on. And there are 3 properties of these, there are 3 such meso properties that I'll focus on, and I'll try to show why they're so important. So why meso level analysis? Well, in a sense, people who come from an engineering background will be familiar with this. This is the so-called block modeling approach. So if you want to understand a computer, you could, of course, try to look at in terms of the transistors and the diodes and so on, but it will be a horrendously complicated description. Instead, you would rather want to have a hierarchical description where you, at the coarsest level, you kind of break it up into blocks. So you say, okay, so you have, let's say, a central memory store, you have a secondary storage which is kind of slower than the central memory store or the ROM, and then you have a control unit which could be connected with the arithmetic unit, and this constitutes the CPU, and then you would have input devices connected to the main part of the computer, and then output devices which is giving the response and so on. And then each of these blocks in turn you can further subdivide into sub-blocks, and those sub-blocks could be analyzed still further. Finally, you go all the way to transistors and diodes. So the idea is like, can we have a coarse-grained description of a complex system where it's not, you're not going down to the most elementary level because it will be too complicated description, but rather groups of those elementary units which you can consider as a block and then see how these blocks relate to each other. Okay? I hope that this will become clearer as we go along. So before we go into the proper meso-level structures, let me say that even something like degree, you can actually look at a property which is not global, nor is it quite an micro-level property. So if you look at a degree of a single node, it's a micro property. But if you look at degree distribution, that's a global property because you're talking about the entire network's distribution of connections per node. But you could be interested something beyond that. You could ask, what is the correlation of the degrees? So, do high degree nodes preferentially connect to high degree nodes, or is it the opposite? In a social context, this will be like asking, do popular kids preferentially become friends with other popular kids, or is it the other way around? Now, you might say that, okay, that's pretty simple, right? I just go around and asking how many popular kids know other popular kids, but there's a catch there. So, if you are looking at whether the popular kids all know each other, because each popular kid has lots of connections, just by random chance, if you start connecting them up, the chances are that popular kids will all be connected because anyway they have large number of connections. So, you have two nodes, each having, let's say, hundreds of connections. And even if you randomly connect them, it's very likely that they'll get connected. You are asking that beyond random chance, do you see a higher than random chance of them being connected? Okay. So you're basically correcting for this probability of just randomly connecting two high degree nodes and asking that, is the actual number of connections that you see even more than what you would expect by chance? Only then you would say that's a statistically significant high probability of connections occurring between popular nodes. In contrast, if you find that typically low degree nodes tend to prefer to high degree nodes and vice versa, again you will have to show this against a random null model. That you would have to show that compared to what you would expect at random, the probability that a high degree node connects to a low degree node is higher than what you would expect from chance. So how do you go about it? So you look at degree correlation where you ask that what is the probability that a link connecting nodes of degree k and k prime would be higher than what you would expect by pure chance. So this is like, if there was no correlation, this is what you would expect. Now, there are multiple ways of measuring this correlation and they all go by the name of assortativity or a degree assortativity. So, assortativity is a term which is very common in sociology, which basically says that individuals prefer to associate with individuals having similar traits. Okay. Now, this similarity in trait need not be number of connections. So, it could be similarity in terms of gender, similarity in terms of age, similarity in terms of cultural tastes. Okay. You could measure assortativity in any number of ways, but the easiest thing to do in networks is just to look at their, sorry, that's not my video, right? Okay. So, the simplest thing is to look at degree. Okay. So, we simply ask that, is the probability of connecting to another node associated with the degree of these nodes. Okay. You could look at other network properties. So, for example, you could ask, do high clustering nodes prefer to connect to high clustering nodes, or do high centrality nodes prefer to connect to high centrality nodes? So, these will also be different types of assortativity, but I will just deal with degree assortativity because that's the simplest and the most dealt with. Okay. So, how do you measure it? So, one common measure is this kind of a correlation measure called the assortativity, which was proposed by Newman. I won't go into the details of this, you can look it up anywhere, and anyway most graph theory toolboxes would have a module for calculating this. Suffice it to say that if this quantity R is 0, it means that there is no correlation. Okay? There is no preference as such of nodes of a certain degree to connect to nodes of certain other degree. I mean, they are connecting effectively at random. But if R is less than 0, then you have an anti-correlation. This is called disassociative mixing. In other words, nodes of high degree are actually preferentially connecting to nodes of low degree. And you will see this in mostly biological and technological networks. Okay. So, why is that the case? Let me come back to that after I talk about associative mixing. So, in associative mixing, R is positive, and so here like prefers like. So, and this is, for example, seen very often in social networks. People who are gregarious, extroverts tend to prefer people who are also gregarious extroverts, okay? And so you would find that nodes of high degree have nearest neighbors of high degree. Okay? Now, it has often been speculated that why is it that other than social networks, we tend to see disassociative mixing. So it has been argued that one possibility could simply be that having associative mixing in technological or biological networks leads to instability. So, to give you an example, if you have nodes with many connections connecting to node with many connections, disturbances or perturbations can actually quickly bring down the entire network. So, for example, if you have a airline network and you would notice that the first, so like there's fog in Delhi, let's say this time of season you mostly have fog in Delhi, and you go to catch your flight from Chennai to Bangalore, and you are told, sorry sir, your flight has been delayed, and you ask why, and you said there's fog in Delhi. Yeah, excuse me, I'm not even going to Delhi. So, well, it turns out that even though you're not going to Delhi, the airline network is so densely interconnected that, let's say the flight from Delhi got delayed and the bay in which your flight, which will go to Bangalore, is supposed to arrive, is now occupied by the flight from Delhi. Okay, or maybe the plane which is coming from Delhi is going to be, turned into the flight from Chennai to Bangalore. So, typically, if you have such airport hubs being connected to each other, very quickly a perturbation, a disturbance like a fog in one of these hubs gets transmitted very quickly to the rest of the network. So, one way to counter that is to not have the hubs directly talk to each other, but rather through low degree intermediaries. So, that increases the robustness or the stability of the network. So, this has been argued as to why, yeah? Yeah. So, if you have a situation where you have hubs directly talking to each other, any congestion that happens in this high degree nodes would very quickly spread through this, subnetwork of high degree nodes all talking to each other to the rest of the network. Okay. Whereas if you have high degree nodes insulated from each other by low degree nodes, okay, you could always take action at the low degree node point such that the disturbance remains confined to that high degree node where it originally originated. Okay, or it's at least slowed down so that the system has a chance to correct the effect of these perturbations. Okay, whereas if all the high degree nodes are connected, before the system has a chance of like correcting for these congestions and delays and so on, it's already spread throughout the network, and eventually the whole network grinds down because of the congestion. Okay, and the example I was giving of congestion is this airport network problem. Typically, because all the airport hubs are connected to each other, like Delhi, Bombay have very high degree of connectivity, as it does with Chennai and Bangalore and so on. So, even early in the morning, when the planes are just starting out, you feel the effects of this fog in Delhi first in the hubs like Chennai and Bangalore and so on, before it starts making its effects felt in other areas such as Trivandrum and so on. Okay, so it starts spreading very quickly. That's what I meant. Okay, so that's one of the reasons why people think that disassociative mixing is, very commonly seen in biological and technological networks, whereas in social networks where you want things to spread very quickly, often like information and so on, you have assortativity. And you can see the difference in the architecture of assortative to disassortative networks in these two schematic pictures which I've taken from Newman's book. So notice that both the networks have the same degree distribution, but the connectivity pattern is very different, which is visually apparent. So here you can see that here in the middle, all the high degree nodes are all connected to each other. So they form what is known as a strongly or densely interconnected core, and the rest forms the periphery, which is kind of loosely connected to the network through one of the densely connected nodes. Okay. Again, social networks actually show this. So you have a very densely connected core of very popular gregarious people, and then there are these shy individuals who kind of are tenuously connected to the network through just one or two friends. And often in when you are trying to do social engineering, let's say you want to make people adapt a particular custom. For example, in Africa, when the WHO wanted the midwives who work with the village women who are expecting, so they wanted the midwives to take up some safe practices such that the newborn child doesn't get infected. And so the question was, how do you actually get midwives to adapt such customs? Now you might say, okay, you just tell them and they'll just do it. It doesn't work that way. Okay, so it turns out that who you target is very important. So if you target popular people in that network, so the midwives form a network, and you try to get the more popular people to basically agree with you. So you have to invest a lot of effort. So you have to select some people. You can't just go to everyone and say. So you have to convince them, work with them for a while. So instead of focusing on the isolated individuals like this, if you focus on the the most popular individuals, the practice quickly spreads within the core, and then they will spread outward into the periphery. So that's a much more efficient way of making people adapt certain practices than working with individuals who are on the periphery. And this also works with advertising and marketing. So if you want to start people adapting new product, you kind of focus on influencers and youth leaders. So you do this kind of a market research where you ask who are the most popular individuals in college, right? And you give them free samples. At least that's the way it happens in some places in the US. So they target these individuals who are conceived of as the trend setters in their peer groups, and you try to get them to take your product. And once they start using this product, it kind of gets disseminated into the rest of the campus. Okay. So people actually use this ideas of network theory to do some pretty practical stuff in marketing and so on. And on the other hand, if you have negative correlation, you can see that the network is characterized by this hub and spoke modules, where you have certain popular individuals who are just associated with lots of less popular individuals, and you can see they are not directly, the popular individuals are not directly connected to each other. So you have essentially small communities or small groups where there is one do they call this large fish in a small pond or something? So each of these individuals are like the large fish in their own small pond. They are the most popular person. Everybody looks up to them. Okay, but maybe to protect their highly powerful positions, they don't want to associate into large groups, because then their brand value would be kind of diminished, right? So they form some semi-isolated groups, and then this less popular individuals certainly have a very important role. They help to connect these otherwise disconnected groups to the rest of the network. Okay. So it goes without saying that the dynamics of information diffusion that will happen within this kind of a positive correlated network would be very different from a negatively correlated structure. And a large part of what we do in our network studies is to understand what are the consequences of having this structure versus this structure in terms of stability of the network. Okay. So for example, ecosystems often have a negative correlation, and we would like to understand why. Okay, that what is it that actually leads to evolution of such networks. All right, now to talk about the three basic properties or three basic types of mesoscopic organization networks, let me demonstrate them schematically. So I already told you about adjacency matrices, right? So what I'm doing over here is showing you a schematic adjacency matrix where red indicates very dense connection and yellow indicates very sparse connection. So how do you read this? Okay, so let me go here. So suppose I have a adjacency matrix which looks like this. So this is very densely packed with ones, and this region is more or less sparsely connected. So this is mostly zeros and these are mostly ones. Can you conceive what the network would look like? 4 clusters, absolutely correct. So if the off diagonal blocks were all zeros, so let us suppose these were all 0. Okay, then this would correspond to 4 isolated subnetworks which have no connections with each other. So I can draw them like this. Yikes. So this will be 1. Sort of like this. Okay. Is it clear why this picture of networks is related with this adjacency matrix? Anyone? Okay, fine, good. Now, instead of it being completely 0, I introduce a few ones here and there. Okay. So now suddenly what happens is that I am starting to connect these modules. But you can see that the density of connections within each module is far higher than the density between the modules. So that means that this network has a modular organization. Okay. So these are called modules or communities, and this will be very familiar with anybody who has been in a social setting would be familiar with this, right? There are these clusters of friends. When you go to a new institution, this is very apparent, right? There's this clusters of friends and it's very hard for you to break into it. So you feel so alone, right? Because these people have known each other already for a very long time, and you're not looked at kindly, right? So then it takes a while for you, but eventually you form your own group, right? So each of such groups of friends basically can be thought of as a cluster. All right, so that's the network representation of a modular network. Each is basically a group which is tightly connected to each other, and then they're loosely connected to other groups. The other kind of organization would be what I would call hierarchical. So again, I'm representing it through an adjacency matrix like this. So what do I mean by this? Okay, so let's look at okay. So now what I'm doing is I'm actually doing something like this. So what does this mean? So now this is mostly 0, these are mostly 1. So can you say what the structure would be like? Sorry? Exactly. So now I can think of 3-layered network. Looks a bit like your multi-layer perceptron. Okay, where the links are essentially from one layer to the next layer. Okay, you could of course have a few ones here and there, which would mean, so if it's within the same block, that means there are a few connections within each layer, or if there is a connection here, that would mean there could be a few shortcut connections from here to here and so on. But dominantly the connections are from one layer to the adjacent layer. Okay, so we call this hierarchy, where this is the first level of the hierarchy, this is the second level of the hierarchy, this is the third level of the hierarchy. Okay, so that's why, if I just look at 2 layers, then schematically this is what it would look like, and this is how a typical hierarchical network looks like. You have several layers and the nodes are arranged in each of these layers such that connections go from one layer to the next adjacent layer mostly. The third architecture that has this meso level, that I would call a meso level property, is the core periphery structure. So what is core periphery? Again, let me show you by okay, so this would be very dense, connected with ones. This would be a little less dense, this would be even less dense, and then finally this is even less dense. What kind of architecture would this be? Yes, absolutely right. So this would be a extremely tightly coupled thing that everyone's talking to everyone. And then the next layer, there is some connections within them, but not much. Okay, maybe like this. And then the next layer, even less connections, and so on. Okay, so you can actually think of it as an innermost core which has the densest connections, everyone's talking to everyone, and then successively, it's like an onion. You peel an onion, you go from the outermost periphery to the innermost core, which is almost fully connected, whereas the outermost periphery, they don't have too much interaction with each other. They mostly connect to each other by going into the innermost core and then coming out again. So in order to find how they connect to each other, you have to actually trace their connection all the way to the innermost core and then out again. Okay, and this is how many of our social networks work like. So this is sometimes also known as a rich club. Okay, you might have heard the word rich club coefficients and so on. So rich club is not very different from this idea of this core periphery. Okay. So let me first start with core periphery organization. So this is a schematic of a network where, intuitively you might say that this is the core and the outer part is the periphery. So there is a way of treating this quantitatively where you say that you can define the K core of a network as that subnetwork which contains all nodes that have degree at least equal to K. Now, often I have students at this point saying, hold on a second, isn't that same as just looking at all the nodes which have degree K or more? So, yeah, so they say that, look, suppose I have suppose I'm looking at a node of degree, suppose I'm looking, trying to find a core of degree 3. So they say, okay, I just look at all the nodes which have degree 3 or higher. So that means, so these have, so they will say, okay, this will be the core of degree 3 because each of these nodes have degree 3 or higher. Okay. Problem is that if you look at the definition, it says all nodes that have degree at least equal to k, and so we will see that actually that doesn't qualify. So to see why that is the case, we will do something called the k-core decomposition. So this was a procedure actually suggested by Seidman back in 1983, who said that look, if you really want to identify a k-core, you can go like this. You do an iterative process where you first remove all nodes having degree less than k. Now if that was the only step, then of course my student would be right that you just look at all nodes having degree k or higher, but that's not where you stop. So after you have done that, you check the resulting network to see if any of the remaining nodes have now become less than k, and then you remove them also, and you keep repeating this until you find that all remaining nodes have degree at least equal to k. So let's look at this.
So this is the definition of k-core then, like the thing that you get resulting from this process?
No, actually that definition is completely consistent with this. This definition is not any different from that. It's just an operational way of finding the k-core which satisfies this property.
It has to be a subnetwork.
Yes, it is a subnetwork, but the point is that all the nodes, I mean when you discard all the nodes that are already with it, the ones which are left, which are connected, should have degree k after you remove the nodes which do not contribute to the core.
So it's an induced subgroup where each of them have degree at least k.
Yeah, correct. So here for example, the problem is, although you think that this is part of the core, the problem is if you look at just the core itself, it does not have a degree, it has a degree of only 1, right? So it does not satisfy the definition of k-core. Okay. So how do you go about this? So according to Seidman's proposal, what you do is as follows. So first, in order to find the one core, so by the way, what is the one core for this? Can any of you say? So again, let me remind you, what is the way to do one core? Remove all nodes having degree less than k, check the resulting network to see any of the remaining nodes have degree less than k, and if so, repeat the steps until all remaining nodes have degree at least equal to k. So what will be the one core? The entire connected component, which is what I've drawn. Okay, so that's kind of trivial. What about two core? So once you have two core, so you have to remove all nodes which have degree 1. Okay, so remove this, remove this, remove this, remove this, remove this. Okay. Also I think this, right? Yeah. But now you check the network and you see that this network which originally had a degree of 5 now has a degree 1. So you remove this also. And now you are left with just this. Okay. So this is the 2 core. What about 3 core? It's also the same, right? What about 4 core? Null, right? Yeah. Okay. So that's why it's not the same as just looking at the subset of nodes which has degree k. Okay. Because you have to look at that subset where if you discard everything else, all the nodes have degree at least k. Alright, is that clear? Okay, so I'm just repeating this here. So this is one core, then you remove all the nodes which have degree less than 2 iteratively, and you are left with 2 core. And the interesting part is that you'll find that if you have a k core, there will exist at least k paths between any pair of nodes. So then you are left with a 3 core, and then there's no 4 core. Okay. So one example of this is the network of interbank borrowing. So this is a data set which was shared with us by someone who was working in the University of Essex, and she wanted to know whether there is any particular property of interbank borrowing which makes certain banks more susceptible to collapse than others, because then in that case you can identify the bank as being contributed to systemic risk, and then impose a tax called centrality tax by which the bank would have to give this much money, so that if it fails, that money could be used to rescue the other banks. So when we looked at this network, we found that it had this kind of core periphery structure where, by the way, the size of the nodes correspond to like how much asset holding the bank has. So in some sense, it corresponds to how rich the bank is. So not surprising, the richest banks formed a very densely connected core where they're all borrowing from each other, and the less powerful banks basically form a periphery where they're loosely connected to the rest of the network. So then we tried out a simulation of banking collapse, where we said that suppose we take any one bank in this core and we say that let's say it declares insolvency. So which means that it says that we cannot honor the commitments we made because we simply don't have money. So it closes shop. Now this will result in trouble to the rest of the banks. Why? Because the other banks who have lent it sums of money suddenly find that they can't honor their commitments. And if the amount of assets they have cannot balance for the shortfall, then they will also have to declare insolvency. And very soon you get a cascade, right? And this is what essentially corresponds to systemic risk in the banking system. As a result of one bank collapsing, the contagion spreads to the rest of the bank, where bank after bank basically fold. So it becomes even worse as it goes along, right? So if one bank fails, maybe it won't cause too much of a shudder. But if 2 or 3 banks fail, what will happen is that combined loss will not be absorbed by the rest of the banks, and they will also start failing one after the other. And so one of the questions we asked was, what happens if the periphery banks fail versus the core banks fail? Okay. So it turns out, not surprisingly perhaps, that if something happens to the periphery banks, it's not going to affect the rest of the system. But if something happens to any of the core banks, it can very quickly take down a large chunk of the banking network. And so the policy decision that could be taken is, we impose something like, instead of a centrality tax, a core membership tax to the core banks, where they are forced to pay the regulatory authority some money owing to their position in the network, which can be used as a reserve to bail out banks in the event of a systemic failure. Okay. So this is one of the practical things you can do with core periphery. Another very interesting paper that I wish I had done this work. So for Bollywood, in fact, actually, so currently as we are speaking, one of my postdocs is actually doing the very similar kind of thing for Bollywood, but with a slightly different twist. So this paper was actually done by Sandor Juhas et al. In 2020, where they started looking at the collaboration network in the Hungarian film industry. So here the nodes are not just actors, but it's also directors, producers, music directors, and so on. So basically talents. And the idea is, like, if they have collaborated in let's say n number of movies in the last 10 years, you connect them. So basically it says that they have been collaborating with each other very strongly and so on. And what they found was that it has also a core periphery structure, and it correlates very well. So the people who win the awards tend to be the ones who connect lots of peripheral nodes to the core. Okay. Now, they don't have a causal explanation as to why this is the case. This is just something they are seeing. There is a strong correlation between your position in the core periphery. So if you're a bridge who happens to, so you may be part of the core, you may be part of the periphery, but the important part is, are you a bridge who is bridging lots of periphery nodes to the core? If you're a bridge, the probability of you winning an award is extremely high. So one of my postdocs is now doing this for Bollywood, where our question is not award winner versus non-winner, but asking, can you identify a subset of nodes who are strongly correlated with high box office returns? So in other words, if you have this director, this music director, and this actor, are the chances very high that over this time, all the movies they have made have actually earned high box office returns. Needless to say, this is something that many production houses are actually very interested in, this question. You would love to know that if you combine this director with this music director with this actor and so on, you got a relatively modest hit in hand. Alright, so modules. So what are modules? As I already mentioned, these are communities which are kind of, strongly intraconnected, but relatively weakly interconnected. Okay. So modules are defined by, the fact that they have very dense interconnections within themselves and relatively few interconnection between modules. And you see modular networks everywhere, essentially, not just in social network, but for example in biology, if you look at the metabolic network, so this is basically the nodes are various metabolites. So they could be lipids, they could be fatty acids, amino acids and so on, and the links are basically telling you, are they involved in the same metabolic reaction or not? And what you find is the modules, so here the nodes are not themselves shown, rather what you see in the circles are the modules themselves, and the modules are color coded according to what kind of metabolism they are involved in. So what you find is that even though this is a module defined purely on the basis of networks, so if lots of connections exist within a module, then you define a module, but you can also see that there is a very strong functional association. So there are some modules which are primarily dealing with amino acid metabolism, the green ones. There are modules which are primarily associated with carbohydrate metabolism, the yellow ones. And there are modules which are primarily dealing with nucleotide metabolism, like this, sand colored ones. Then if you look at, for example, food webs, again you see that, the species kind of divide into groups which are very strongly interconnected within each module and relatively very weakly interconnected across modules. Social networks is an obvious example. So this is the social network of a particular village in Karnataka. So the way we got this data is actually very interesting. So Abhijit Banerjee actually had a paper in Science in 2013 where he was looking at, the role of microfinance in promoting entrepreneurship in villages and what is the role of social networks in that. Okay. So he used a set of data which was collected not for the specific purpose of his paper. There was an NGO called this Bharat Swamukti Samasthe, which was a microfinance institution. And what they did was, in order to find the feasibility of, starting their business in various villages, they went to about 90 villages all around southern Karnataka and did this survey where they would go to every individual and ask, who are your family members? Which temple do you go to? Who are the other people who go to the temple? which shopkeeper do you mostly deal with, who are your friends. So like various kinds of networks, friendship networks, exchange networks, like who do you lend money to, then family networks. I mean, family networks, not just immediate family, but also kinship, your uncles, your cousins, and so on. So you have like, maybe 10 different kinds of networks they have information about. And they collected all this to basically ask, so if you construct a network on basis of this, you try to find out who are the people who are most densely interconnected in the network. Why is it important for them? Can you guess? Why would a microfinance institution be so interested to know the social network structure of a village?
They could help you grow they could help you popularize things.
Yeah, but that's not the main reason. Anyone?
To understand their, whether to lend loans or not.
Why?
To look at their credibility towards a bank.
Exactly. So the thing is, if you lend money to a loaner who doesn't have too much connection to a village, the person can do a, like a quick, cut and run job. Okay. Whereas if you are, if your entire family is like central to the village, your uncle is the panchayat head and your mother is basically, connected to lots and lots of family members all across the village. Even if you run, they can get hold of your entire, family and eventually make sure that they get the money back. Okay. So you're a much safer bet to lend money to if you're strongly connected to the village network rather than if you're on the periphery. Okay. So that was their interest in doing all of this. Unfortunately for them, after doing these surveys, they lost so much money, they went out of business. So fortunately, they had all of this data in digital files, and somehow Abhijit Banerjee managed to get hold of it. And then we are grateful to Abhijit Banerjee because he and Esther Duflo actually put up the data online as part of the online repository of the paper. So one of my students got hold of this data, and we are always data hungry, right? Because data is so hard to come by. So we found this enormous amount of data and we said, wow, let's do something with it. And the first thing that my student did was to actually do a modular analysis. And he found that actually the village has a large number of groups, effectively 25 modules. The largest having 127 members and mean average module size of 47 members. And the colors actually represent the different modules. Okay. Now, one thing I should make it clear that this network is basically a combination of all the 10 different individual networks that they looked at, which was kinship network, who trades with who, and so on. So you might argue that, is this really, the true picture because you are condensing everything into just a single network. It could be much more, nuanced, like the Medici network, So some families could be related to another family because of marriage, but other family through, temple, going to the same temple and so on. We would love to do that analysis, but this data set is so rich, you can do lots of things, but given a finite time and finite number of PhD students, there's only so much you can do. So we looked at some interesting behavior, including epidemic spreading in this network. So, but even before we get into that, the question is, so you've got a network. Now, how do you find the modules into which it can be divided? So I said 25 modules and you just nodded your head. You just took my word for it, right? You could have simply said, how do you know there are 25 modules? Okay. And if truth be told, I cannot, cross my heart and swear to die, because depending on what technique I use, it will actually be different. Okay. So all we can do is, it's actually turns out it's an NP-hard problem, finding the number of modules. Okay. So what you can do is you just try several methods and try to find a consistent set of modules which will agree across different methods. That's the best you can do. Okay. So So community detection networks is one of those problems which unfortunately physicists were not the first. It actually started in computer science. Okay. So if you look at like your standard CS books, you'll find it referred to as graph partitioning problem. And so the way that it's defined in CS textbooks is usually like this. It says that suppose you have a graph like this. How do you divide the nodes of a network into groups such that each group is very strongly or densely interconnected? And usually it's done like this. You try to find a partition such that that partition cuts across the fewest number of links. Okay. So in this case it's pretty obvious, right? It's here. So visually it's pretty clear that this forms a module and this forms a module. And if you draw the corresponding adjacency matrix, not surprisingly, it will look almost block diagonal, right? So it will effectively look like that. So A to E will be dense with ones and F to J would be dense with ones, and there's only one connection between them two, D to F. So if you look at D to F, this will be 1 and this will be 1. The rest are all zeros. Okay. Okay. Now you'd say, okay, pretty obvious, except that this is not so obvious once you have 100, let alone 1000 nodes. Okay. Try drawing this network and try to figure it out. Okay. Not possible. So you need some algorithmic way of finding the modules. Okay. So this is a classic problem, as I said, and from the 1960s, computer scientists have been actually working on this. So how do you divide the nodes of a network into a number of non-overlapping groups such that the number of edges between the groups is minimal? Okay. And generalization of this problem is that you divide the nodes into several groups such that most links are within groups, few links are between groups.
And we specify the number of such communities, right, for a given number of communities K.
Good point. The simplest version of the problem is you try to do it by bisecting it, graph bisection, right? But in general, you don't know how many modules there are. Okay, and that is the most general problem, that you don't know how many modules there are. How do you actually approach the problem? So the classic algorithm that I will talk about, graph bisection, that says, okay, bisect it and then take each of the separate things and then again try to bisect them and keep doing this until you can go no further. But that leads to a problem. It's the same problem as, what do you call, so if you try to do optimization by doing gradient descent, you'll get stuck at a local minima. It's the same problem. You might get stuck at a local minima. You will not be able to find the most optimal solution because you are doing this bisection one by one. Okay, so that's why it's not a surefire way of finding the modules.
Even for two partition bisection, it's NP hard.
No. Two-part is fine. Two-part is fine. But in general, when you don't know the number of modules, that's when the reality bites. Okay, graph bisection is easy.
Minimizing the number of crossing.
Yeah. That is pretty easy because it's got a very nice. So you basically just find the large eigenvector corresponding to the largest eigenvalue. Okay, it's a very simple linear algebra problem. Okay, so it turns out that this, how you define most and how you define few is what actually differentiates one community detection method from another community detection method. Any community detection method you see basically just boils down to defining most and few in a particular way. So I won't go into this classic graph bisection problem because of lack of time, but I do have a tutorial method, tutorial set of slides which someone can actually maybe do during the tutorials okay, which kind of goes through this in great detail. So instead of that, I will come up with another thing where instead of trying to give an algorithm, what Newman did was he proposed a metric. He gave what is known as a modularity index. So what is a modularity index? It simply says that compared to random chance, how many more links do you have between nodes in the same module? So again, think about it. So if I have I connections, if I have ki connections and you have kj connections, then the probability that if you and I are in the same module will be connected is proportional to ki into kj. Got that? Just by random chance. Because the probability that you and I will be connected is proportional to the product of your connections, number of connections, and my number of connections. More connections you have, more connections I have, higher the probability that you and I will be connected, right? So that's the probability that you and I will be connected simply by chance, even though we are in the same module. I have to compare that against the empirical frequency of connections within a module. So what I do is I go across all, so first you say that let me guess a particular modular organization. So what you do is you take some partitions that may be correct, may not be correct, and you compute this quantity where you said, okay, what's the actual number of connections of members within a module, and subtract from it the number of connections of members within the module you expect from pure chance given their degree. Okay? And you look at this difference. And you ask, how large is this number? The bigger the number, that means the more chances that this is a module, because there is higher than random probability that two nodes within the same module are connected. Everyone with me, or is this confusing? Yes, no, yeah.
Sir, so Aij is the probability of two nodes inside a module being connected.
Aij is simply the adjacency matrix, so it gives you the actual frequency. Okay, Aij is the empirical information. Ki into kj by 2l gives you the probability that just by random chance you'd be connected, and you are summing this over all modules. So delta ci cj simply says that only those ij's will contribute which according to my partitioning belongs to the same module. Alright, okay. So for a random network, by definition this will be 0, because any connections that I have will be entirely governed by the ki kj probability. Okay. The bigger this number is, that means the more this is deviating from randomness. So basically what I have to do is maximize this index. That partition for which q is maximum is the actual community organization. So you will say, okay, now how do I, this is like a circular problem, right? So in order to find this, I have to know the right partitioning. Well, think of it another way. This now gives us a way of turning the problem into an optimization problem or a maximization problem. So now we will use our favorite optimization routine, simulated annealing or extremal maximization or whatever, or genetic algorithm. The problem is simply this: I make a random guess, I find q, then I make a change to my guess, see if q becomes larger or smaller, accept that or not, and then keep doing this over and over again until I can improve this guess no further. Okay? So now this turns into an optimization problem. And you can lose any of your well-known optimization routines onto this. Okay? So this is what is used in the literature very often. Another, and actually you can generalize this also for weighted and directed networks. Another method which has been also used a lot is using a slightly different approach. So here the fundamental idea is like a modular structure actually allows you to optimally compress the information describing the network. Okay, so suppose you are, you have the entire description of the network and you want to turn it into a encoded message which has the least size. So if it has any structure, then you can use that to compress this information. Instead of giving the entire zeros and ones, you could just simply say, okay, from row 1 to row n, it is all ones, and from row n plus 1 to row m, it is all ones, rest is all zero. So that's a extremely tight description compared to actually giving the entire matrix, right? So you have used the modularity property to compress the information. So the idea goes that, can you actually use this modularity property to compress the information? So the more you can compress, so you try out various partitionings and you see what is the smallest compressed description you can make of the network, okay, lossless compression, okay. And so using this approach, you can also try to find the best modules. And it turns out that this method that I told you about, the spectral method proposed by Newman and this method proposed by Roswell and Bergstrom, actually have a quite consistency, quite high level of consistency with each other. Typically this information flow method gives you more modules, but it turns out that they are just splitting the networks that the modules you find from the Newman measure, okay. So there is a level of consistency. In other words, even though the number of modules is different, you can actually see them as just fine splitting of the modules that you found using the Newman method. So that's typically what we do. So I mentioned, right, that I have a collaborator who works on macaques. So he works mostly in the Bandipur forest area. Bonnet macaques are, of course, the most common monkey, right? They're seen across all cities. I'm sure they're around in Ahmedabad also. And they live in large groups. Typical size is about 40, and adults are about 10. And they have very, very strong relationships with each other, okay? Now, how do you actually define social relations between macaques? What kind of interactions?
I'm reading the slide, but is it like if they pick their license from their head or something?
Very nice. So this is known as allo grooming as opposed to self grooming. So allo grooming. So it turns out when we used to first learn about grooming, we thought it's all about hygiene, right? They're just doing this for hygienic purpose. It turns out it's much more than that. Allo grooming is equivalent to gossiping. Okay, they can't speak. Instead, so grooming is a very versatile kind of communication medium. It's like Bengali saying acha. We see acha in all kinds of, when in doubt say acha, right? So, so if you want to show care, if you want to say I'm not a threat to you, or if you want to say that, will you support me if I, try to take on the head guy, what you do is you spend a long time allo grooming the other individual, okay? So it's a very, very, versatile way of forming bonds, social bonds, okay? And you could, just as, you can use the how many times you telephone versus how long you talk in a telephone. These could be two very different measures of how strongly connected to an individual, okay? So you might be like taking a minute call. So my friends in Finland who actually did this analysis for telephonic networks, they said that, they had this huge data set of people calling each other, and they found that they had these people who have, done 200 calls per day, and but each of the calls were of like a minute or 2 minute duration, and they didn't know what to do about it, versus people who might have done just 2 calls a day, but each call was 1 hour, okay? So what do you make of these? Is the first type of person more gregarious than the other person, or more socially connected? Well, it could be just a telemarketer, right? Doing 1 call, of 1 minute duration, but 200 such calls. It doesn't mean, I mean, a telemarketer doesn't have any social capital whatsoever with the person that he or she is calling, right? Whereas that person who made 2 calls, but each caller was 1 hour, maybe was talking to his girlfriend, right? And that of course meant significant investment in time and effort. So this frequency and duration are 2 complementary kinds of measures. They can't be interchanged with each other. So that's why you look at both grooming frequency, how many people are you grooming, versus how long are you taking to groom them. Okay. So those are 2 complementary types of information. And approach frequency is like, how frequently are you approaching a person. I remember I mentioned that they have this very, very strong hierarchy where only the dominant individual can actually approach a subservient individual, not the other way around. Okay. So if a dominant individual approaches a subservient individual, means that maybe this person actually likes that other individual or whatever. So another thing is that we refer to numbers, right? Now these numbers mean what is their rank. Now you might say, okay, how do we even know rank? That's because in primate societies, especially among the female primates, rank is pretty much determined from birth. Okay. So it turns out if you are the youngest daughter of the dominant female, you're automatically number 2. Don't ask me why youngest. I mean, this is the first thing that occurred to me when I heard this from my primatologist collaborator. Why youngest? I would have thought it was the oldest. But turns out it's the youngest daughter who is always number 2. And then the next youngest and so on. Okay. So, and this also goes on to like your aunts and cousins. So, like first the dominant female, then the youngest daughter, and then the rest of the daughters. Then comes the aunt, who is of course the older sibling of your mother, and then their children and so on. So this is how it goes. But of course, sometimes you may not know all this. This can only be obtained genetically, right? If you do genetics. So how do you actually empirically find out who's the most dominant? Well, you just observe. So you find that always the dominant individual is going to get her way in an exchange with the less dominant individual. Now you might say, okay, I can figure out how you do this if it's just 2, but then how do you do it for an entire troop, right? So let's say you have A, B and C individual. So let's say you figure out that A is dominant to B. Okay, and let's say you find that B is dominant to C. Okay, to assign a unique rank, you must have one more property. That is, if A is greater than B and B is greater than C, it should automatically imply that A is greater than C. And transitivity, exactly, you need transitivity. And it turns out that this is true. So this is always true. Okay. And so therefore you can assign a unique rank, okay, to the primates. So here the numbers actually refer to the rank where 11 so 11 was dominant. And so over a period of 4 years they did this recording. So what happens is every morning one of the graduate students picks a random number from 1 to 11, and whichever number peaks, that will be the animal that will be followed for 1 hour duration. So every other individual that this particular animal interacts with is noted down, and then next day they start with another animal and so on. So this is called focal sampling and so on. If you do it in a zoo, of course you can just take video cameras and record it, but in a zoo the behavior will be completely different. So you can't really replace observation of animals in captivity versus animals in the wild. So these are all animals in the wild. Alright, so Anindya, who was my collaborator, gave this data set to us and said, well, can we actually see something interesting from this network? Now, I mentioned that the female networks are very stable. So once the assignment of rank is done after birth, it remains stable throughout. But for males, that's not true. So today's king can, happen something like this, your hand is broken, tomorrow you are number 10, okay, because you can't fight, okay. So it's very unstable. They constantly get challenged by younger males, and you have to really fight hard to remain the top dog, all right. So what we did was we took this network and we did community detection, and this is what we saw for the female network. So you notice that across all the networks, grooming frequency, grooming time, approach frequency, you find consistently that individuals 1, 3, 4, 5, 6 form one module, 2, 7, 8, 9, 10, 11 form another module. Remember, 11 is the most dominant, 1 is the least dominant. So you can see it's not exactly numbered. So number 2, for example, is actually part of the other group, whereas 1, 3, 4, 5, 6 is part of the same module. Compared to that, the males, it's all over the place, right? Every parameter we use gives rise to a different module, so which kind of says that it's actually unstable. But something more interesting. So when we notice this, we realize that there is a consistent, modular partitioning of this network, and if there's only maybe a few connections holding this network together. So when we went back and looked at it, we found that somehow this node 1, even though it's the least dominant, is somehow holding the rest of the network together. So we went back to Anindya, and Anindya kind of said, wow, this is really interesting stuff, because I didn't share with you the data from 98. So when they went back to 98 and looked at the group, it had actually split into 2 parts. In the meantime, between 97 and 98, this least ranked individual 1 had died. And so the group split into actually 2 groups. So this group 11, 10, 9, 8, 7, 2 went their own separate way, and 6, 5, 4, 3 went their own separate way. So in some sense, 1 was the cement that had bonded these 2 groups together, 2 modules together into one cohesive group. The moment 1 died, they actually split apart. So what was so special about 1? 1, you remember, was the least dominant. So it turned out that 1 was the agony aunt. You get beaten to pulp by your mother, you go to 1 to get, groomed and say, oh, nothing will happen, your mother will love you again, and so on. And since she was the least dominant, nobody felt frightened. Okay, so she was in some sense holding the entire group together. So talk about soft power, this is soft power in action. Okay, so she didn't have the power of rank, but she managed to hold the group together. Okay, Amit, is that a warning that I should wrap up soon, or?
Oh, no.
Okay, okay. So I will just skip through the rest of the slides because this was just a technical point to show that actually if you look at modular networks in terms of these kinds of model networks where you have a block diagonal structure and then you gradually increase the ratio of the intermodular connections to intramodular connections, you can actually show that they have exactly the same property in terms of how the path length and clustering coefficient behaves as a function of the inter to intramodular connection density, as in Watt-Strogatz network you get with the fraction of long range shortcuts. So what we are doing here is that we are varying the ratio of intermodular connection density to intramodular connection density. So when R is 0, that means all the connections are within the modules. When R is 1, that means all the connections are distributed all over. So that means this intermodular connection density is same as intramodular connection density, so that's why it's homogeneous. So as R increases from 0 to 1, you go from a completely modular, isolated modules to a perfectly homogeneous network. So what we find is that if we look at it as a function of R, then exactly in the way the Watt-Strogatz network behaves, your the average path length kind of, so this is the inverse of the average path length. So when the communication efficiency increases, it means the average path length is actually decreasing, and similarly the clustering coefficient is also decreasing in a way very similar to Watt-Strogatz network. So this basically told us that if you find a network with a small world signature in terms of how its average path length and clustering coefficient is behaving, it does not automatically mean it's a Watt-Strogatz kind of model. It could also be a modular model, modular network model. But then comes the question, okay, if you can't tell apart a Watt-Strogatz network from a modular network using the structural measures, what do you do? So it turns out that if you use dynamics, in other words, if you look at how, let's say, synchronization or diffusion or ordering in such a network behave, then Watt-Strogatz network and modular networks behaves extremely differently. So what you find, for example, when you are looking at synchronization, is that in the Watt-Strogatz network, things synchronize more or less around the same time. Everything synchronizes all at once. It takes a long time, but it eventually synchronizes. But if you look at a modular network, there are two time scales. First, you have the elements within each module synchronizing, and then the modules synchronize with each other. So you have two time scales, a time scale at which you get global synchronization and a time scale at which you get modular synchronization. And the interesting part is that as you gradually decrease R, so when R is 1, it's completely homogeneous. When R is 0, it's completely isolated. So as you gradually decrease R, it becomes more and more modular. You find that the time to achieve global synchronization diverges, whereas the time to obtain modular synchronization does not change all that much. And so just by looking at how long it takes to synchronize the entire network, as you change the modularity coefficient, you can actually tell whether it's a modular network or not. So for example, I mentioned the Karnataka network. So here you can see this propagation of epidemics, and you find that this behaves actually very differently from a homogeneously connected network, because the infection tends to stick around within a module for a long time before jumping to another module, and this means that when they jump to another module, it takes a long time to circulate through the entire network. So by the time it comes back, some of the individuals have already started recovering, and so the epidemic has another chance to go around the entire network. So this is very important for diseases like COVID, where you don't get permanent immunity. So it means that as the pathogen is going around and around the network, if it is a highly modular organization, the disease will never completely go away. It will just keep circulating. Whereas if you had a completely homogeneous network, there were no modular organization, you will just have a one giant spike where everybody gets infected all at the same time, and then because the pathogen doesn't find any susceptible individual, it will just disappear. Okay, so it turns out that epidemics would have very, very different behavior in a modular social network versus a homogeneous network. So modularity actually promotes persistence of pathogens, where in the empirical network of the Karnataka network, it just keeps going on and on and on and on, whereas in a corresponding homogeneous network, it will just have a one giant spike and then disappear. And you can explain this by looking at how diffusion occurs in a modular network. So you have two time scales, a fast intramodular diffusion time scale and a slow intermodular diffusion time scale. And in modular networks, the disease spreads slowly from module to module, thereby allowing other parts of the network to recover before it spreads. So I won't go into the details of this maths, you can look it up from my notes. Suffice it to say that you can actually connect it with the eigenvalue spectrum of the corresponding Laplacian. If any of you have questions, I'll be more than happy to discuss it after the class. And so the question was, okay, how about real small world networks? Are they actually better explained by modular architecture? And since we showed that the modular architecture is evident from this gap in the Laplacian spectrum, we obviously looked at all these brain networks, looked at the Laplacian spectrum and found out sure enough you have this gap, okay, which is indicative of model organization. And it also tells us something, that you will have very fast synchronization within each module, but the network structure prevents abnormal global synchronization, which would lead to abnormal activity like epilepsy. So that's architecture that nature has come up with to protect the brain against epileptic like seizures, but at the same time allow synchronization within local regions, which is necessary for information processing. This is just to show that real brain. So this is the brain of a macaque, showing the various areas, brain regions, and the colors represent the various modules that we have identified. And we can actually see model organization, and the model organization are actually also related to function. So for example, if you look at modules 1, 2, 3, 4, 5, module 1 is mostly associated with olfaction, that is the sense of smell and taste. Module 2 is associated with somatosensory motor sensations. 3 is associated with emotional responses and formation of memory. 4 is associated with auditory, hearing, and 5 is associated with visual. So you can clearly see that the modules which were purely identified on the basis of structural information are also strongly associated with functions. And there is some work that one of my students did which showed that this particular architecture which you find in the macaque brain allows for very, very fast spreading of information, faster even than a corresponding random network. So what is hierarchy? So this is kind of a term very familiar to us because we are often very familiar with social hierarchies, right? And if you remember your high school history, you probably remember charts something like this, that medieval societies were typically structured like you had the king at the top, and then directly under him were the nobles, and the nobles had retinues of knights, and knights each had holdings of land where they had peasants. Okay, so it was a very strictly tiered system. So the peasants owed their allegiance to the particular knight whose land they worked on. The knights owed their allegiance to the noble who had given them their land, and the nobles owed allegiance to the king. So essentially, you had interaction only between subsequent layers. The king had very little to do with the individual peasants, right? So another example is food webs. Okay, so food webs typically are divided into various layers, so which are known as trophic levels, and the base is formed by the primary producers, plants, right? Because they use sunlight to produce food, and then the next layer is what is known as primary consumers. So primary consumers eat plants, and then you've got secondary consumers, those who eat the plant eaters. Then you've got tertiary consumers, and so on. Okay. So again, most of the interactions are between successive layers. Okay. So I mean, omnivores like humans are an exception. Okay. So if you look at ecosystem, typically you find that, so this is essentially the primary producers or plants, then the primary consumers, so this is sheep or whatever, rabbits, then you got wolves or something else which feeds on them, and then you got tertiary consumers, those who feed on the secondary consumers, and so on. Of course, humans, so mostly you have, or rather the arrow is actually directed the other way, because we say that the arrow basically says which way is energy flowing. Okay. So if A is B, the energy flow is from B to A. Okay. So you have energy flowing like this. Of course, you need not just have one particular food. So you could have, for example, something could be feeding on lots of other things and so on. But then omnivores have this ability that they can feed from many different layers. Okay, so but omnivores are actually somewhat rare. The reason why omnivores are actually rare has been speculated a lot. Usually it's argued that in order to be able to eat anything and everything, you actually require a very complex metabolic machinery. Whereas if you are specialized in eating just one particular kind of food, you can have a much more simpler metabolic system. So there's this trade-off between having simple versus complex metabolism and the ability to eat across different kinds of trophic levels. So this is another example of what do you call it, hierarchical system. So another example is of course the brain. So if you look at the brain, the classic cartoon of a brain is that, well, you have these inputs. So typically these are the sensory neurons which are connected to your sensory organs, and then you have lots of interneurons, and then finally you've got this output of the motor neurons which will give the impulses to the muscles, right? So this of course is the what you call the architecture of deep learning neural network. Okay, so you got input layer, hidden layers, and output, but it didn't come out of vacuum. It's actually inspired by what is actually seen in the brain's architecture. So you have some stimulus which goes into sensory neurons, which is then processed by interneurons, which is then acted upon by motor neurons, which then leads to some action. All right. So the question is, how do you actually uncover this hierarchical organization? Just as in the case of modular network, the question was, I give you a network, but then how do I find the modules? The same question you can ask here. Okay. So for example, in the book Connectome by Sebastian Seung, he actually makes this point that, look, we know that in certain types of songbirds, there is a particular kind of neuron called HVC neuron, which is arranged in a sequential ladder kind of thing. Okay, and this allows the bird to actually remember a sequence of vocal, muscular movements to be made, which results in a very prototypical song. Okay, I mean in utterance like, and then other birds will go and so on, right? So these are very, very characteristic of that bird. And so the way this is done is by having a set of neurons arranged in this way, such that the sequential activation of this neuron one after the other causes the vocal muscles to contract in particular ways in which this prototypical sound is made. Okay. So we understand that it must be done by this kind of a sequence of neurons. I mean, it doesn't look like a hierarchy, but it is a hierarchy in the sense that there is a ordered arrangement of the neurons such that activation of one causes the activation of the next layer, causes the activation of the next layer, and so on. So for network purposes, this is a hierarchical network. The problem is, unless you already know the architecture, and I just give you it in some kind of a tangled form. Actually, this network and this network is the same. Okay, I've just tangled it up. It will be very hard for you to, from this, figure out that it's actually like this. Okay. Okay, here you might still get it by trial and error, but imagine you are trying to do this for 100 nodes. Okay, it's going to be really tough just doing it manually. Okay, so the question is, how do you do this for a reasonably large network? Okay, it's the same issue that we face for modular network actually. So this is something you can, so this is actually work from my lab. So a former student of mine, Anand, actually started working on this problem, and he came up with a very, very intelligent way of, looking at this problem. So he said that, look, just as we use a modularity index for modular networks, maybe we can use a hierarchy index for hierarchical networks. And the way he did that, you can see that there are nice analogies with the modularity index. So he says that, well, in the hierarchical network, the connections are mostly across successive layers. So what I will do is I will ask that if I look at a node I in layer I, if I look at a node in some layer, let's say n, and a neuron in the layer n plus 1, then I ask, is there a connection between them? And if a connection exists, the frequency of connections, is it more or less than what I'd expect by pure chance? Now, how do I find what is the probability that there will be a connection between them by pure chance? I simply look at the degree of one of the nodes, degree of these two nodes, take the product, divide by the total number of connections, and that will give me the probability that just by chance this node here and this node here would be connected. So, by looking at the difference of the actual empirical frequency of such connections from what I'd expect by random chance, and considering only the connection between successive layers, I can actually define a hierarchy index in analogy with what we had for modularity. So then it becomes again a question of optimization. So what you do is you start with a guess, then you calculate the age, and then you try to maximize it by doing a number of possible steps. So you can either, for example, merge two randomly chosen levels, or you can move a node to a randomly chosen different level, or you can split a randomly chosen level into two successive levels, or you can exchange the order of a pair of randomly chosen levels. Okay, so there are each of these can be taken up with equal probability. So you do these moves, and then you again calculate age, you find whether it has increased or decreased, and then you probabilistically accept the move or reject the move, and you keep doing this until you go from something which looks unstructured like this to something structured like this. So you have found the most hierarchical arrangement that is possible from this particular given network. Okay, so this is kind of similar in spirit to modularity. And then now if you look at the macaque brain, you find that you can actually order them into a sequence of 16 hierarchical layers, and they are pretty robust in the sense that if you keep doing this over and over again, this operation. So remember, this is a stochastic operation, right? Because which move you pick, which node you move from one layer to another, or which level you split, this is completely randomly taken, and so each realization will give you a slightly different hierarchical arrangement. So what you find is that across these different realizations, the membership of the different hierarchical levels remains fairly robust. And so this gives one confidence that this is a fairly accurate representation of how exactly the nodes are arranged in some kind of a hierarchical sequence. Now, one of the consequences of this is that it shows that there are two distinct streams of signals which are propagating parallel across the brain. So one we call the upstream pathway, and so it goes from what is known as the occipital lobe to the temporal lobe to the frontal lobe. So the occipital, as you can see, is located here, and the temporal lobe is here, and the frontal lobe is here. So this is the what you call the upstream pathway, and then there's a downstream pathway where you go from frontal lobe to parietal lobe to occipital lobe. So it's the reverse way. So frontal, parietal, occipital. And so this is actually very similar to this model of bottom up and top down processing working in conjunction, which has been proposed for vision and which has been tried to be implemented in many models of computer vision. So you require so when you see a picture out in the world, the network essentially tries to process it, but it also has to give back feedback, okay, all the time to the top layers. And these are going on simultaneously, the feed forward and the feedback. And so this is interesting that the hierarchical architecture of the brain that seems to be revealed by this algorithm actually supports a similar kind of mechanism going on in the actual brain. Okay, so I have an assignment for looking at some of these, like for example, how do you actually find mesoscale architecture. So hopefully this can be, Amit, this can be done during the tutorial session, this assignment. So I also have the answer associated with it, so those who are running the tutorial can actually consult the answers and help them. Okay, good.